Welcome to Math Fair. I'm your instructor, and today we're going to build mathematics from the ground up. Get ready for an incredible journey where we'll prove 11 fundamental theorems that form the backbone of algebra. Before we begin, let's recall the 6 fundamental axioms that are our foundation. Axiom 1 is the commutative property, x plus y equals y plus x, and x times y equals y times x. Axiom 2 is the associative property, x plus y plus z equals x plus y plus z, and x times y times z equals x times y times z. Axiom 3 is the distributive property, x times y plus z equals x times y plus x times z. Axiom 4 establishes the identity elements, x plus 0 equals x, and 1 times x equals x. Axiom 5 guarantees the existence of negatives. For all x, there exists a y such that x plus y equals 0, and Axiom 6 guarantees the existence of reciprocals. For all x not equal to 0, there exists a y such that x times y equals 1. We also have 4 previously proven theorems. Theorem 1.1 is the cancellation law for addition. If a plus b equals a plus c, then b equals c. Theorem 1.2 establishes the possibility of subtraction, given a and b. There exists a unique x such that a plus x equals b. Theorem 1.3 defines subtraction. b minus a equals b plus negative a. And theorem 1.4 is the double negative. Negative negative a equals a. Now let's begin with our new proofs. Theorem 1.5. A times b minus c equals a times b minus a times c. This is an extension of the distributive property. Proof. We start with a times b minus c by theorem 1.3. This equals a times b plus negative c. Applying axiom 3, the distributive law, we get a times b plus a times negative c. By sign rules, this equals a times b plus negative a times c. Finally, by theorem 1.3, this equals a times b minus a times c. Therefore, we have proven that a times b minus c equals a times b minus a times c. Theorem 1.6, 0 times a equals a times 0 equals 0. Proof. Consider 0 times a plus 0 times a. By the distributive property, this equals 0 plus 0 times a. Since 0 plus 0 equals 0, this becomes 0 times a. By the cancellation law, we conclude that 0 times a equals 0. By commutativity, we also have a times 0 equals 0 times a equals 0. Theorem 1.7, the cancellation law for multiplication. If a times b equals a times c, and a is not equal to 0, then b equals c. Proof. Given a times b equals a times c and a not equal to 0. Since a is not equal to 0, we can multiply both sides by a inverse times a times b equals a inverse times a times c. By the associative property, a inverse times a times b equals a inverse times a times c, since a inverse times a equals 1. 1 times b equals 1 times c. By the identity property, b equals c. Therefore, the cancellation law is proven. Theorem 1.8. Division always exists. Given a and b with a not equal to 0, there exists a unique x such that a times x equals b. The solution is x equals b divided by a equals b times a inverse. Proof of existence, let x equal b times a inverse. Then a times x equals a times b. Times a inverse equals b times a inverse equals b. Times 1 equals b. Proof of uniqueness. If a times x1 equals b and a times x2 equals b, then a times x1 equals a times x2. So x1 equals x2 by theorem 1.7. Theorem 1.9. b divided by a equals b times a inverse when a is not equal to 0. This theorem follows directly from theorem 1.8. Since b divided by a is defined as the unique solution to a times x equals b, which is precisely b times a inverse, Theorem 1.10. A inverse equals A, when A is not equal to 0. The reciprocal of a reciprocal is the original number. Proof. We need to show that a times A inverse equals 1. But this is exactly axiom 6. Since reciprocals are unique, we conclude that an inverse equals a theorem 1.11. The zero product property. If a times B equals 0, then A equals 0, or B equals 0. This is the foundation for solving equations. For example, if x times x minus 5 equals 0, then x equals 0, or x equals 5. Proof by contradiction. Assume that a times b equals 0 and a is not equal to 0. Since a is not equal to 0, we can multiply by a inverse. Times a times b equals a, inverse times 0 equals 0. Associativity, a inverse times b equals 0, which gives us 1 times b equals 0, therefore b equals 0, theorem 1.12. The sign rules. Negative a times b equals negative a times b, and negative a times negative b equals a times b. These are the famous rules. Positive times positive equals positive. Positive times negative equals negative. Negative times positive equals negative. And negative times negative equals positive. Proof of the first part. Negative a times b plus a times b equals negative a plus a times b equals 0 times b equals 0. By the uniqueness of negatives, negative a times b equals negative a times b. For the second part, negative a times negative b equals negative a times negative b equals negative a times b equals a times b. Theorem 1.13. Addition of fractions. A over b plus c over d equals a times d plus b times c, all over b times d when b and d are not equal to 0. For example, 2/3 plus 1/4 equals 2 times 4 plus 3 times 1, all over 3 times 4, equals 11/12. Proof. A over b plus c over d equals a times b inverse plus c times d inverse. This equals a times b inverse times 1 plus c times d inverse times 1. Substituting 1 as d times d inverse and b times b inverse respectively, a times b inverse times d inverse plus c times d inverse times b inverse. This simplifies to a times d plus b times c times b times d inverse, which equals a times d plus b times c, all over b times d. Theorem 1.14. Multiplication of fractions. A over b times c over d equals a times c over b times d when b and d are not equal to 0. The rule is multiply numerators and multiply denominators. For example, 2/3 times 4/5 equals 8/15. Proof. A over b times c over d equals a times b inverse times c times d inverse equals e. Times c times b inverse times d inverse equals a times c times b times d inverse equals a times c over b times d. Theorem 1.15. Division of fractions. A over b, all divided by c over d, equals a times d over b times c, when b, c, and d are not equal to 0. This is the famous multiply by the reciprocal rule. Proof. A over b, all divided by c over d, equals a over b, divided by c over d, equals a over b times c over d inverse equals a over b times d over c equals a times d over b times c. Congratulations. We have proven 11 fundamental theorems that form the foundation of all algebra. We've proven the extensions of the distributive law, the properties of zero and cancellation, rules of division and reciprocals, the sign rules, and fraction. Arithmetic. These theorems allow us to manipulate algebraic equations with complete confidence. Don't forget to subscribe to MathVer. Like this video, comment, and share it with others. We're building mathematics one proof at a time. See you in the next video, where we'll continue our mathematical journey.